All right, let's just dive right into this explainer and demystify the everyday magic of how a completely normal metal box uses advanced thermodynamics to keep all our food fresh. I mean, it's sitting right there in your kitchen, humming away, yet most of us totally take for granted the incredible physics happening inside.
So, have you ever actually wondered how your fridge keeps food perfectly cold on the inside, but if you walk by it, it's blowing warm air on the outside? It's a pretty interesting paradox, right? You put room temperature groceries into an enclosed space and boom, an hour later, they're perfectly chilled. But feel the back or the sides and you get a wave of warm air. How can one single machine be freezing cold and noticeably hot at the exact same time? Well, today, we're going to look past the mundane exterior of this appliance and uncover the fascinating engineering that makes that possible.
Here's our roadmap for this explainer. First, we'll cover the magic of cooling. Then, we'll meet the core components, walk through the actual refrigeration cycle, look at how modern frost-free tech works, and finally, explain exactly why your fridge feels warm to the touch.
Kicking things off with Section 1, the magic of cooling and moving heat.
Okay, so here is the absolute golden rule of thermodynamics when it comes to your kitchen. You cannot actually create cold. Seriously, cold is simply the absence of heat. So your refrigerator doesn't just, pump cold air onto your food out of nowhere. Instead, think of it as a highly efficient heat sponge. It actively absorbs the heat from your food and the air inside the box, which is what slows down bacterial growth, and then it literally pumps that heat out into the surrounding environment. Moving on to Section 2, meet the core components, our mechanical heroes.
There are 4 main components that make up the closed-loop system of your fridge. First up, we have the compressor. This acts as the heart of the system, vigorously pumping a special fluid, a refrigerant, throughout the loop. Second, the condenser coils. These are basically the lungs on the outside of the fridge, breathing out the heat. Third, the expansion valve, which is a tiny but absolutely critical gatekeeper that meticulously regulates pressure. And finally, the evaporator coils. These sit inside the fridge and do the heavy lifting of actual heat absorption.
And this brilliantly illustrates the big divide between the inside and the outside of your appliance. You've got the evaporator coils on the inside, soaking up all that thermal energy from your leftover pizza and fresh veggies. Meanwhile, the condenser coils are located completely on the outside, usually on the back or tucked under the bottom, actively releasing that exact same heat right into your kitchen. They are literally 2 halves of the same continuous loop, just moving thermal energy across a physical barrier.
All right, Section 3, the refrigeration cycle explained. Think of it as the hero's journey.
Now, this whole cycle relies entirely on changing the physical state of the refrigerant, like R134A, for example, from a liquid to a gas and then back again. It starts with compression, where low-pressure vapor is squeezed into a high-pressure hot gas. Next is condensation, where this hot gas flows outside, cools down, and condenses into a liquid, releasing its heat. Then comes expansion. The high-pressure liquid squeezes through a tiny valve, experiences a massive pressure drop, and turns into a freezing mist. Finally, evaporation. This cold mist flows through the inside coils, absorbs heat from your food, boils back into a vapor, and heads right back to the compressor to start the whole thing over. If you're kind of struggling to visualize what the compressor is actually doing, just think of a simple bicycle pump. When you forcefully pump air into a bike tire, you are doing physical work, right? You're compressing that air. And what happens to the metal base of the pump? It gets hot. Well, the compressor in your fridge is doing the exact same thing to the refrigerant gas. It uses mechanical energy to squeeze the gas, which forces its temperature to spike way above room temperature. And that's exactly what allows it to shed heat to the outside air later in the cycle.
Now, on the flip side of that, we have the expansion valve. To really understand this one, think about cleaning your computer keyboard with a can of compressed air. After a few seconds of spraying, you'll notice the can becomes freezing cold in your hand. This perfectly demonstrates what physicists call isenthalpic expansion. By forcing the high-pressure liquid refrigerant through a tiny pinhole, the pressure instantly plummets. The sudden expansion forces the liquid to flash into a low-pressure, incredibly cold mist. It's just an elegant, simple piece of engineering that triggers the whole magic of cooling. Looking directly at this PV, or pressure volume diagram, we can actually map the backwards Rankine cycle we just talked about. Check out the path from point 3 to point 4. That represents the expansion valve. It's an adiabatic throttling path, which is really just a fancy way of saying the total heat remains perfectly constant. No heat is added or removed, but because the pressure drops so drastically, the temperature of the fluid plummets to well below the temperature inside your fridge. Let's move to Section 4.
how frost-free technology works and solves ice buildup.
So for a really long time, humanity basically wrestled with thick, solid ice buildup on evaporator coils. But modern engineering solved this with a trifecta of clever designs. First, an automatic defrost cycle uses a small heating element that actually turns on periodically to gently melt away any frost forming on the hidden coils, draining the water away. Second, circulating fans constantly push the chilled air around the cabin, which prevents those stagnant cold spots where ice absolutely loves to form. And third, drastically improved insulation stops warm, moist room air from sneaking in through the doors. Together, these features save you from having to chip away ice with a butter knife, all while saving energy and maximizing your storage space.
Finally, Section 5. Why your fridge feels warm. Some everyday observations.
Okay, we've all done it. You lean against the side of the fridge or grab the space right between the freezer and fridge doors, and it's surprisingly hot. After everything we just learned about cooling, this might seem a bit alarming, right? Like, is the motor overheating? Is the fridge working too hard? Well, rest assured, this is perfectly normal. It's entirely by design. That heat you feel on the sides is simply the condenser doing its job, radiating the heat it pulled out of your groceries into the room via heat dissipation pipes built directly into the sidewalls. Furthermore, the area right between the doors often has a literal heating wire embedded inside the frame. Because the cold air inside meets the warm room air right at the door seals, condensation and water droplets would constantly form there. So the heating wire gently warms the metal to keep it dry and prevent mold. It's an incredibly smart, totally hidden feature.
So as we wrap up this explainer, I want you to look at your refrigerator just a little differently. By mastering the delicate dance of pressure, liquid, and gas, this machine hasn't just given us a way to keep milk from spoiling. It leads us to a much bigger question. How has this century-old thermodynamic cycle fundamentally reshaped global food supply chains, modern medicine, and human comfort as we know it? Next time you grab a cold drink, take a second to appreciate the silent magic making the whole thing possible.